Hi physics class, today we're going to talk about the Doppler effect. Okay, if you've ever noticed the sound of sirens, they change when they pass you because of the Doppler effect. I know I've noticed that. Have your ears open when you're outside and you'll experience that too. And I'm going to explain why that happens. So if a source of waves approaches you, the source catches up to the waves it's producing. So let's say this is producing sound. Sound just goes off in all directions at a constant frequency. But if the source of sound is moving, it catches up to the sound in front of it. And actually behind the object, the sound's going to be more spread out. Okay? If you're traveling the speed of sound, what happens is you are always caught up to your sound, and in front of you, you have a great deal of sound in one location, whereas behind you, it's really spread out. Okay? This region of all the sound when something's traveling the speed of sound is a sonic boom. So when you pass it, you pass through the threshold of all this sound you've created in a great deal of time. It's a great deal of energy and it's loud. You've definitely heard a sonic boom, maybe from the jets that fly overhead us every so often. Also, the crack of a whip is a sonic boom. In any case, for our purposes, we just need to realize when a source of sound, the Doppler effect applies to all types of waves, but we're just going to limit to sound for our discussion, is approaching you, the waves kind of pile up on each other, and you detect a higher frequency. Actually, if you're behind the object moving, you'll detect a lower frequency. Okay, so I'll link a video of an ambulance driving by. As it's getting closer, you're hearing a higher frequency. Once it passes you, the frequency changes much lower, which sounds deeper. Okay. Here's the formula that we're going to be working with, and it's a unique formula in that there's a plus or a minus. I'm going to tell you what all of these symbols mean. Vs is the speed of the source. Okay, V is the speed of the wave. And we're usually using sound, so that can be confusing. You might want to make Vs speed of sound, but it's not. It's the speed of the source. Okay, so the frequency Fs, that's the frequency at the source. It's kind of like the true frequency. And F is the detected frequency. Now you'll notice there's another interesting feature of this formula. There's a plus or a minus. We use one for approaching and one for receding. Okay, as things are approaching, you detect a higher frequency. That'll occur when you divide by a lower number, which is subtracting. So use subtraction for sources approaching. And use addition in the denominator when the source is receding, so moving away from you. Okay, so there's a lot that goes into that simple little formula. It's not too bad though. Okay, so I've set up an example here. I'm saying a police car approaches at 30 meters per second. This is the true frequency of the sound. We're going to determine the frequency we detect as it approaches and as it recedes. So we just have to remember when approaching, we got to subtract the speed of the source. Okay. You need a speed of sound. Let's make the speed of sound equal to 350 meters per second. Yeah, I'll include that in a question. I just forgot it in this example when I was setting it up. Okay, so let's do it. V is 350. Vs is 30. And Fs is 200. Okay, so I'm going to do 350 divided by 350 minus 30. Make sure that's in brackets. Multiply that by that frequency 200. I'm going to get, we'll call it 219 hertz. As it's receding, we just do the same thing, but we add in the denominator. We should get a lower frequency, which we do. It's 184 hertz. One thing I just want to point out is the true frequency was 200, And it is not like an equal shift, receding and approaching. Okay, so it goes up by 19, and then when it passes you, it goes down by 16. So it'll never be equal. That looks pretty good.